Today we are going to talk about the circular motion, and this is a very important topic. So if we just look at some examples of circular motion, we'll come to know how important it is. So for an example, if we take a stone tied to a string and whirl it in horizontal circle, it's one of the examples of circular motion. Then another example could be motion of an electron in an atom. Okay, so according to Bohr's theory of an atom, electrons revolve around the nucleus in circular orbits. So if we understand circular motion, then we will also understand something about the atoms. Then another example can be motion of planets around the sun. Okay, so circular motion has got vast number of applications, okay, many number of applications, and that's why it is very important topic. So now, what is circular motion? So circular motion is obviously a motion of an object around circumference of a circle. Okay, so now let's talk about some basic terms and definitions related to circular motion. Now let's suppose this object which moves along circumference of this circle in, let's say, anti-clockwise sense. It starts from this point, let's call it A, and it goes to some point, let's suppose it goes over here. If this object goes from A to B, then the angle subtended by the path of this object, which is the arc on the circle, so angle subtended by that arc at the center of the circle is known as angular displacement. The direction changes if you look from my side or if you look from the other side. Okay, so if it's a vector, then it should have a definite direction. So we cannot just say anti-clockwise or clockwise. Okay, because from my side if it is anti-clockwise, then from the other side of circle it will be clockwise. And that's why what we do is we define its direction using a rule known as the right hand rule. Okay, so what is right hand rule? So take your right hand, curl fingers of your right hand in direction of motion of this object. So if you are looking from this side, okay, then it will be anti-clockwise. So curl fingers of your right hand in anti-clockwise sense and then stretch your thumb. Okay, so your stretched thumb will denote the direction of the angular displacement. Okay, so now if you use this convention, then no matter from what direction you are watching this object, the direction of angular displacement will be just same. Now, as angular displacement is the angle subtended by path of the object performing circular motion at center of the circle, we can define angular velocity. So what will be angular velocity? So we define angular velocity omega as angular displacement divided by the time. Okay, so let's suppose time taken by this object to move from A to B is delta t, that is time taken by the object to perform angular displacement of delta theta is delta t, then the angular velocity is given as angular displacement divided by the time. And since angular displacement is a vector quantity, its direction is given by the right hand thumb rule. The angular velocity is also a vector quantity, and that's why we put an arrow on top of this omega. Okay, this letter which looks like a W, it is known as omega. Okay, so omega bar is the angular velocity and it is delta theta bar divided by delta t. Okay, then just similar to a linear motion, okay, a change in velocity with respect to time gives us acceleration in linear motion. So similar to that, we can define angular acceleration also. So if angular velocity of this object changes, okay, with respect to time, So angular velocity at this point is suppose omega 1, angular velocity at some other point is suppose omega 2. That means if this object speeds up or speeds down, then we can define angular acceleration. So angular acceleration is denoted by alpha bar equals to omega 2 minus omega 1, omega 2 bar minus omega 1 bar divided by t2 minus t1. Okay, so it is just change in angular velocity with respect to the time, where omega 2 is angular velocity at time t2 and omega 1 is angular velocity at time t1. So this can be written as delta omega bar divided by delta t. So these are the average values of these quantities. So just like linear case, here also we can define the instantaneous values of angular velocity and angular acceleration. So instantaneous angular velocity will be what? So instantaneous angular velocity omega bar will be equal to limit delta t tends to 0 of delta theta bar by delta t. Okay, or it is just derivative of theta bar with respect to the time, and the instantaneous angular acceleration can be defined as alpha bar equals to the derivative of angular velocity with respect to time. Okay, so this is about angular velocity and angular acceleration. Now we said that the direction of the angular displacement is given by right hand thumb rule. So right hand thumb rule is, take your right hand, curl the fingers of your right hand in direction of motion of the object along the circle and stretch your thumb. Okay, so your stretched thumb gives you the direction of angular displacement. Now since the angular velocity is just angular displacement divided by time, the direction of angular velocity and direction of angular displacement will be just same. Okay, so direction of angular velocity and direction of angular displacement is same. But what about angular acceleration? So here, because we take subtraction of two angular velocities at two different times, so if angular velocity is increasing, then alpha bar will be in direction of angular velocity, and if it is decreasing, then it will be in opposite direction to that of angular velocity. Okay, now let's talk about the acceleration in circular motion. Okay, so if object moves with constant speed along circumference of circle, then that circular motion is known as the uniform circular motion. And if the speed of object changes, then the circular motion is known as the non-uniform circular motion. Okay, so here onwards we'll talk about the uniform circular motion. So again, let's consider an object performing circular motion. So here is object at position A, O is the center and R is the radius. Now how can we find out the speed of this object? So we know speed is distance covered divided by time taken. So let's suppose the object is performing uniform circular motion. So speed is given by distance covered divided by time taken So in one revolution, the distance covered by this object is 2 pi r, and time taken by this object to complete one revolution is known as the time period of this object. Okay, so it is known as time period of the uniform circular motion is equal to 2 pi r divided by t. All right, then now what is relation between the frequency and time period? So frequency n is reciprocal of time period. All right, so number of revolutions performed by an object per unit time is reciprocal of the time period. So frequency n of this object is equal to 1 over t. Okay, so now let's find the relation between linear speed and angular speed of this object. So linear speed and angular speed. Okay, so if this object moves along circumference of the circle and if it completes one revolution, then how much will be the angle covered in radians? So we know angle equals to arc upon radius. Okay, so arc length is for one revolution. So for one revolution, angle covered will be equal to what? Arc length 2 pi r divided by r. Okay, so r and r gets cancelled out. So angle covered is 2 pi. And suppose this is theta. Okay, so what is the angular velocity or what is angular speed? So angular speed omega is angle covered divided by time. Okay, so for one revolution the angle covered is 2 pi and time taken is the time period of the revolution. Okay, so omega equals to 2 pi upon t. And what is linear speed? So for linear speed of particle performing circular motion, we have this formula 2 pi r divided by t. Okay, so linear speed v equals to 2 pi r divided by t, and if I substitute omega in place of this 2 pi divided by t, we get the relation between linear speed and angular speed. So v equals to, okay, 2 pi by t is omega, so omega multiplied by r. Okay, so this is the relation between the linear speed and angular speed. Motion of an object along circumference of circle with constant speed is known as uniform circular motion. So question is, if there is some acceleration in uniform circular motion or not? So answer is simple. We know that acceleration is change in velocity divided by time. So if we consider any kind of circular motion, so let's suppose circular motion of this object moving along circumference of this circle. So at this point the velocity will be along this direction. Okay, the instantaneous velocity is always tangential to the circle. So at this point it will be directed along this line, okay, along this tangent to the circle. And even if the magnitude of this velocity remains constant, even if this object keeps on moving with constant speed, its direction will change. So as we can see, if this object goes at this point, then its velocity will point in this direction. Okay, so this is suppose VA bar and this is VB bar. Now nobody will say that this VA bar and VB bar is same. So in uniform circular motion, the magnitude of velocity, which is speed, remains constant, but there is change in direction of velocity, and that's why there is change in velocity, and that's why we can say there is acceleration. Okay, so uniform circular motion is an accelerated motion. So the acceleration is always directed along the radius and towards the center of the circle, and that's why it is known as the centripetal acceleration. Okay, so in uniform circular motion, the acceleration is always directed along the radius and towards the center. So it is center seeking acceleration, or we also say it is centripetal acceleration, or also the radial acceleration. Okay, so now what we are going to do is we are going to derive an expression for this centripetal acceleration. So let's do that. So let me copy this diagram from here. Suppose this object moves from this point A to point B on circumference of this circle. So if we join these 2 points A and B, okay, we get this triangle OAB. All right, so this angle is the angular velocity. It's the magnitude of angular velocity for this object, and suppose it is theta. Okay, so now what I want to do is I want to find out the change in velocity of this object when it goes from point A to B. So since this is uniform circular motion, there is no change in magnitude of velocity, and there is only change in the direction of velocity. So what I will do is I will take this VA bar and I will put it over here. Okay, so this is my VA bar. Okay, I have put it at point B. Now what will be VB bar minus VA bar? It will be a vector directed in this direction. Okay, so this is delta V bar. All right, using triangle law of vectors addition, we can write. So using triangle law of vectors addition, we can write VA bar plus this vector delta V bar is equal to VB bar, and therefore delta V bar equals to what? VB bar minus VA bar. Okay, so then since the object is performing uniform circular motion, we can say that the magnitude of velocity remains constant. So suppose that magnitude of VA bar is equal to magnitude of VB bar, and suppose that's equal to V. Okay, so now I claim that this angle will also be theta. So if this angle is theta in this triangle OAB, if this angle is theta, then in this triangle, or I would say velocity triangle, this angle would also be theta. And the reason is, in this triangle OAB, the angle between these two radius vectors, so radius vector when the object is at point A, and radius vector when object goes at point B, angle between those two radius vectors is theta. So now we know that velocity is perpendicular to the radius vector. Okay, so velocity is directed along the tangent, and tangent is perpendicular to the radius. So velocity is perpendicular to radius vectors. Now since the angle between two radius vectors is theta, then if we rotate these lines or radius vectors by 90 degrees at both positions, then we will get the direction of velocities. Okay, so if angle between two lines is theta, then angle between perpendiculars drawn to those two lines will also be theta. Okay, if angle between two lines is theta, then the angle between perpendiculars drawn to those two lines will also be theta, and that's why this angle between two velocities, okay, at point A and at point B is also theta. All right, so now I hope it is clear to everybody. So therefore, by SAS test, these two triangles are similar. Okay, since in this triangle length of this side and this side is same, it's the radius of circle, and this angle is theta, and in this triangle, the velocity triangle, the length of this side is magnitude of VA bar, length of this side is magnitude of VB bar. Okay, and since the object is moving in uniform circular motion, the magnitude of VA bar and magnitude of VB bar is equal. So this side is same as that of this side, length is same. So by SAS test, we can say that these two triangles are similar. Okay. So using SAS test, we can say that this triangle OAB, and let's call this one BCD, okay, they are similar. Triangle OAB is similar to that of triangle BCD. Okay, and that's why we can write, so ratio of corresponding sides of similar triangles is equal. Okay, so if I take ratio of this delta V to this side, okay, so delta V divided by V will be equal to what? This length of this side divided by this side. And what is this? So this is, if this is RA bar and this radius vector is RB bar, then this will be equal to what? Change in position vector or change in radius vector of this object. So AB is delta R bar. Okay. So length of, so this vector over here is delta R bar. All right. So position vector when the object is at point A is RA bar, position vector when object is at point B is RB bar. So a vector directed from point A to B is change in position, or it's the displacement vector of this object. So it is delta R bar. All right. So now since these two triangles are similar, we can say that ratio of corresponding sides will be same, and therefore I can write that delta R over R is the ratio of this side to, let's say, this side in this triangle OAB, and it should be equal to delta V divided by V. Okay, ratio of these two sides. So it is equal to delta V divided by V. So since the ratio of the sides, corresponding sides of similar triangles is same, we can write that delta R over R equals to delta V divided by V. Alright, then I can take this R on the other side. So I can write delta R, sorry, I will take this V on left hand side. So I get delta V equals to V times delta R over R. Okay, then what I can do is I can divide this both sides of this equation by delta T. Okay, So dividing by delta t and taking limit delta t tends to 0, taking limit delta t tends to 0, what do we get? We get limit delta t tends to 0, delta v over v equals to v divided by r, limit delta t tends to 0, v divided by r multiplied by delta r over delta t. Oh, I wrote v over here. Okay, so now what I am doing is I am dividing by delta t and I am taking limit delta t tends to 0. So on left hand side I get delta v over delta t, and on right hand side I am writing delta t in denominator of delta r. So now what is this? So on left hand side we got the change in magnitude of velocity with respect to time. So this is magnitude of the acceleration. Okay, and on right hand side we got change in position with respect to time. So what is this? This is velocity. Okay, so limit delta t tends to 0, delta v over delta t gives us acceleration, and this acceleration we got due to change in direction of the velocity. So it is called centripetal acceleration. So I am putting this suffix c over here, and on right hand side we have v over r multiplied by limit delta t tends to 0 of delta r divided by delta t. And what is limit delta t tends to 0 delta r by delta t? It's dr by dt, change in position with respect to time. So it is velocity. Okay, so AC equals to v squared over r. This is one formula for the centripetal acceleration. Now if we substitute v equals to r times omega, we get AC equals to r multiplied by omega squared over r. Okay, so if we substitute v equals to r times omega, we get AC equals to r squared omega squared over r, and the square will get cancelled out with this r. So what we get is r omega squared. Okay, so this is another formula, AC equals to r times omega squared. And also in this formula, if I write this v as r times omega, one of the v as r times omega, I get this as equal to v over r multiplied by r times omega. So this r and r gets cancelled out, and we get another formula for centripetal acceleration. So we get AC equals to v times omega. All right. So we got these three formulae for the centripetal acceleration. We started by saying that in uniform circular motion there is only change in direction of velocity and magnitude of velocity remains constant. Okay, speed remains constant, and considering that only the direction of velocity changes, we found out an expression for the acceleration in uniform circular motion, that is known as centripetal acceleration. Okay, so we found by subtracting VA bar from VV bar, the change in velocity, we divided it by time, and we found that the centripetal acceleration is equal to v squared over r. This is one of the formula for centripetal acceleration. Now question is, what is direction of the centripetal acceleration? So while deriving this derivation, I already told you the direction of centripetal acceleration is along the radius and towards the center. Let's see why this should be the direction. So again, let's consider an object moving along circumference of a circle. Okay, so let's suppose this is the object and it's moving in any direction. Sorry, it's moving in clockwise or anti-clockwise direction, and at this time, suppose its acceleration is directed something like this. Okay, so it is moving, suppose in clockwise sense, and its acceleration is directed like this. So this is my A bar. Now I can resolve this acceleration along two components. So I will resolve it along two components, one along the radius and I will call it AR bar, the radial component of acceleration, and another component will be directed along the tangent. So I will call this AT bar. Okay. So now let's see what will be the purpose of this component. So what will this component do? What will AT bar do? So if there is tangential component of acceleration, we know that in circular motion the velocity is directed in tangential direction. Okay, the velocity is directed along the tangent. So this tangential component of the acceleration will change tangential velocity. Okay, it will change magnitude of velocity. All right. So if this component is present, the tangential component of acceleration is present, then the magnitude of velocity will change. That means the speed will change and the circular motion will be non-uniform circular motion. It will not be a uniform circular motion. Okay. So then what about this other component? So this component changes the magnitude of velocity, and it is only present in non-uniform circular motion, because if magnitude of velocity changes, that means speed changes, and if speed changes, then the circular motion will be non-uniform circular motion. The uniform circular motion is when magnitude of velocity remains constant. Okay, so it means that this component will not be present in uniform circular motion. So what component of acceleration will be present? Only the radial component. All right. So in uniform circular motion, the acceleration is directed along the radius and towards the center of the circle, and therefore we call it radial acceleration or centripetal acceleration. Now what about non-uniform circular motion then? So in non-uniform circular motion, so in non-uniform circular motion, there will be change in direction of velocity. Okay, because particle is moving along the circle, there will always be the change in direction of velocity. So this component of acceleration will be present. Okay, so because AR bar is there due to change in direction of velocity, and in circular motion the direction of velocity changes, and that's why AR bar will be always present. Okay, so radial acceleration will be always present in any kind of circular motion, let it be uniform or non-uniform. But in addition to this AR bar, in non-uniform circular motion, the magnitude of velocity also changes, and therefore there will be some tangential direction. There will be some acceleration in direction of okay, velocity also. All right. So velocity is directed along the tangent, and if magnitude of velocity changes, that means there will be an acceleration along velocity also. and that is tangential acceleration. Okay, so in non-uniform circular motion, a bar, the total acceleration is given by the sum of radial acceleration and tangential acceleration. Radial acceleration changes the direction of velocity and tangential acceleration changes the magnitude of velocity. And therefore, the magnitude of total acceleration will be equal to what? Square root of AR squared plus AT squared, where AR and AT are magnitudes of AR bar and AT bar. So this we know from resolution of vectors. So in uniform circular motion, there is only one kind of acceleration, that is radial acceleration, or we also call it centripetal acceleration. And in non-uniform circular motion, there is radial acceleration as well as the tangential acceleration. Okay. So now I think it's 8:15. Let's stop at this point and we will continue from here next time. Okay. Yeah, welcome. Okay then, bye, good night.